All right, now let's look at the properties of this subset of the n by n matrices, because we gain things and we lose things. One thing that we lose right away is addition. There is no addition defined on the set GLNR. You even know that for 1 by 1 matrices. You could take the matrix 1 and you can add it to the matrix minus 1, and both of those are invertible, and their sum is the matrix 0, which isn't invertible. So there is no addition law. So we lose the vector space, plus or scalar multiplication by 0. If you took a nice invertible matrix and you multiplied it by the 0 scalar, you'd get down to 0, which is not invertible. So forget about addition. However, the beautiful thing is that it's closed under multiplication. Closed under multiplication. It's closed under multiplication. I'll give you two proofs. Here's the first proof. Suppose A and B are invertible. I have to prove that the product A times B is invertible. Well, to prove something's invertible, I just have to find an inverse for it. Can someone suggest what would be a nice left inverse for it? Go ahead. So suppose that...
B raised to minus 1 by A.
Yeah, B minus 1 A inverse exists. So call this, consider this product. And let's multiply it on the left times AB. So I have B inverse A inverse. This is the way it's associated. Times AB. Now, once you have the associative law for three products, you can reassociate for any number of products. That's a nice fact about the associative law. So this can be written as B inverse times A inverse A times B, which is B inverse times the identity matrix times B. Because A inverse, A was invertible, so there's an identity matrix. And then the identity commutes with any matrix, and so this B inverse I is IB inverse. So this is I times B inverse B. And then I associate these two together to get I times I, which is the identity. So namely, this is the inverse. Notice that I have to take them in the opposite order. The inverse is not A inverse times B inverse, but B inverse. And then similarly, if you multiply on the right by this, first you multiply the B times B inverse, that cancels, and then you multiply the A times A inverse. So that's the first proof. Suppose we took this definition of invertible. So we'd have to say that if we had two matrices, each of which had a non-zero determinant, their product had a non-zero determinant. That's what we're saying, right? If that previous condition for invertibility really worked, just being a non-zero determinant, how would we check that? That if two matrices had a non-zero determinant, their product had a non-zero determinant. This is the first proof. And the second proof is there's a famous identity for determinants, that the determinant of a product of two matrices is the product of the determinants. Again, you can never prove that using the definition of determinants as the sum of n factorial terms, but we'll see how to prove that intelligently in a while. Now, if you know this, and each of these numbers are non-zero, the product of two non-zero real numbers is a non-zero real number. So then for this set is closed under multiplication. Exactly. It's closed under multiplication, has a multiplicative identity, which is the matrix I. I times anything is the something times I is itself. Has multiplicative inverses, A inverse, because that's how this set was defined. It's exactly the set of matrices that have a multiplicative inverse. So anything in this set, you can take products. There's a multiplicative identity on the set. Anything has an inverse. And finally, the product is associative. because that was true of the product on the larger set of matrices. AB times C is A times BC. So we have 4 properties of this subset of the set of matrices. It has a multiplication law. The multiplication law is associative. There's an identity element, and there's an inverse for every element. And those properties make up the properties of what we call a group. So this is the first and most important example of a group. So I'll now tell you what a group is. And that's why we need the linear algebra, to generate for us immediately some good examples of groups. I'll give you some more examples, but that's our first example.